Okay, so welcome to the last lecture. I was supposed to have my last lecture obviously before Easter, but because our guest lecturer wasn't able to make it, I've put together this one just on Tesla's Autonomy Day, which happened there last week. So just of the few of you that are in, did any of you get a chance to watch any of the coverage of this, or were you aware of it? No, okay. So Maurice watched some of it. He certainly did, and we'll come up on that. Okay, he certainly did. So, firstly, maybe just to get an understanding of what this day was about, because this was a day to communicate with analysts and investors, really more than the technology community. And this is something that the companies have to do quite a lot because whenever you're pushing the envelope, and all of Elon Musk's companies push the envelope. Be it SpaceX or be it Tesla, oftentimes the payoff, what you're assuming the payoff will be, is an awful long time in the future, or maybe hopefully in the medium term. And for the moment, you've got to spend a lot of money in order to make sure that you're in the right position to capitalize on that. So a lot of that means that you have to have people like investors and so on board. So it was all to do with trying to get that point across, is where they were going with this. And the assumption kind of in the community was that Tesla were a little bit behind some of the others like Waymo and so on, which maybe one of the leaders in self-driving. And what Tesla wanted to say is no, that's not the case. We're actually ahead, and not only are we ahead, but we're uncatchable. Okay, but it is important to understand that this is a narrative that's been given to analysts, as opposed to something like a peer-reviewed paper that you've read, where somebody has peer-reviewed it and give a rebuttal and so on, and where people have to be much more exact. So there wasn't much of a challenge given on these, but of course, in the days that followed, a lot of people have obviously written blogs and videos and so on, challenging a lot of what was being said. For us, what we really need to do is to try and get a sense of what is the key information that we can get out of a day like this. So that what information can we get from it, and maybe try and steer away from anything that is of no particular use to us. Okay, so unless you're planning on investing in some of these companies, some of the predictions for the future, those are generally not something that that we can really rely on, because nobody is entirely certain when you're in such an unusual space as this. Is very, very difficult to say what way is technology going to go, and there are an awful lot of parts with it. But we'll go through each of the different things that was said and try and get an understanding of what we know and what we don't. But I do feel free to ask as much questions as you want. I won't necessarily know the answer because, of course, I'm only basing this on just having watched. It's nearly 3 hours of presentations that went on at it. So here were the main points and claims that they made. Firstly, LIDAR was the big one, really, where he was asked about LIDAR, and he said it was a fool's errand. I think he had various other disparaging things to say about it. But he did also say then, that actually it's not that he's against LIDAR as such. It's just that he doesn't feel that it's appropriate for self-driving cars, and that as part of SpaceX, they had developed a LiDAR for the docking system with the International Space Station, and that they had developed their own LiDAR. So it's not like his companies hadn't worked in that space before or knew nothing about LiDAR and therefore were disparaging it for that reason. They were basically saying this is not the appropriate way to go. And his points were mainly that it was extremely expensive for what it was trying to add, and that he felt that others would drop it. So he was indeed asked, like, well, what about those others in the industry that are using it? He felt that they would not continue with it, and that they would drop it. Now, to bear in mind, LiDAR is all about trying to find out, the distance to some subjects. So it's the very thing that in multi-view geometry we were always trying to compute with camera views, and of course, there are mechanisms to do it. That was the entire point of the module that we just developed. But it was also, there were a lot of difficulties associated with it, and particularly, there were scale problems and so on. But there was, any problem with noise to do with cameras and so on. There were a lot of those issues, and LiDAR and radar get around those problems in different ways. LIDAR suffers from the same problems that cameras will suffer from, in that it can't see through fog and mist and things like that, and radar can. And so the opinion really of Tesla was, well, they have a front-facing radar for that sort of thing. LIDAR isn't really necessary. When people drive, they don't drive with lasers shooting out at their eyes, and they drive perfectly well. No, I think it is important to understand that people don't drive particularly well, and that this is what we're trying to improve on. So just holding up a human, as that's the way the humans do it, does not give us maybe the full answer of where we want to go with this either. So I'm not going to give you the answer as to whether LIDAR does have a future in autonomous vehicles or does not, where it's going to go in the long run. Certainly, if it is to be used in autonomous vehicles, it's going to have to come down in price by a significant margin. Whereas cameras, you can put many of them on your car for very cheap, and that's because cameras already got miniaturized to such an extent that they were in every mobile phone. That's what pushed that forward, and then when that goes into autonomous vehicles or into vehicles in any way, shape, or form, it goes in as a very, very cheap item. And LiDAR obviously is very expensive. It's hard to see where how LiDAR is going to come down in value unless it's as part of vehicles. But even with vehicles which have maybe a 10-year lifespan, you don't have that quick turnaround that you had with mobile phones, which only lasted maybe a year or two, and that you quickly moved on to the next iteration. So LiDAR has certainly problems in terms of how it can really get miniaturized and down in cost. But there are lots of very, very intelligent people working on LiDAR who do believe that it is an essential part of this. And so there'll be... expect that to be a battleground now from here on as regards whether it's the right way to go or not. But some of the other things that they claimed was HD mapping, which is another thing that's very expensive to do, and very expensive to maybe buy off particular companies in order that you have high definition maps. So these are the maps that can tell you not just roughly where you are, but what lane that you're in. Okay, so that you don't get mixed up with the lane that's beside it and so on. And again, they felt that HD mapping, because of the fact that, if you have roadworks or anything like that, or anything changes in the environment, then all of a sudden those HD maps are no longer of use. And that, even with GPS, now again, obviously they use GPS, but they were saying that it shouldn't be a primary feature. You shouldn't be driving blind in that sort of way. That GPS is useful for getting you roughly to the area that you want to go, but that it's not going to be a top feature. It shouldn't be a primary feature. Now, again, there's a lot of people working in HD mapping and GPS. I think they will be useful for all sorts of reasons. And I think, from our own point of view, when we're driving a car, if we've got a sat nav, we're going to look at it, and if we've got a sat nav that tells us what lane we should be in and gives us that information, and it knows that we're in the wrong lane for a turn that's coming up ahead, we always find that useful as humans. The assumption that cars can just get away with computer vision and not have some of that information available to it, it's hard to know. I would certainly have some concerns over that one, even though HD mapping is obviously very expensive to be able to use and to try and keep up to date. I think I wouldn't dismiss it as much as Tesla were dismissing it. But then again, bear in mind that Tesla have gone down a particular route of what they're trying to achieve, and HD mapping is not part of that, and therefore they're clearly going to say that it's not as big of an important to them. So it said humans drive with their eyes, they don't shoot lasers out of their eyes. So computer vision is all that the self-driving car requires, is their claim. Now, when we say that, they do have ultrasonic sensors, and they do have a forward-facing radar as well. But we'll come back to that later as regards their use of the radar and where they feel it's important. They feel that they're in an unassailable lead due to what they call the fleet, and the fleet is that they have almost 500,000 cars. I think it's somewhere up north of 400,000 vehicles that are out there that already have either the new hardware that they've just introduced, or some enough hardware there that they can be taking enough information from road users that are using their cars in order to do all the training that is necessary, and that therefore by having that, that, you know, the company that has the most data is the one that wins, is kind of their thinking. And this is not unusual. I mean, this is why Facebook is offered for free. This is why Gmail was offered for free, and so on. It's all to gather huge amounts of data. So you know, if you ever get a software product and you're not sure what the product is, generally it's you that's of worth to them, not the money that you're not giving them in the first place, because it's free. So therefore, people will often use the users of their product in order to actually gain a kind of a market share, and then become unassailable. And that's the idea that they're trying to push. But again, remember that they're trying to get investors to kind of keep everything going until they can get to this point. They believe that they're going to be a robo-taxi company in the future, not just a manufacturer of cars. And in fact, the manufacturer of the cars is really only to allow them to be a robo-taxi company. And the idea is that when they are at the point where they can become fully autonomous and the regulators allow them, then all of the Teslas that are owned by the public at that time, which they expect to be around about 1 million, then all of those are then capable of becoming robo-taxis with just an update over the web. So in other words, by being able to say that you can, you have all the hardware that you need on the car, and you just put a software update that says you can now become a robo-taxi. Anybody that owns one of these Teslas can, with their standard Tesla app, with maybe just a small change to it, say, I want to release that to be a robo-taxi. And at that point, then, when you're at work or when you're asleep, your car can be out working for you. And then you can just remove it from that network again, then when you want to use the car. And that you would, what they said was Tesla would get 25% of the revenue. So the assumption on that is you would get 75%. But you know, obviously, we don't know within whether this is really workable or not, and we don't know who else would take maybe a taxation share or something else that would come for that in order to be used. Okay. He was asked who would be responsible for an accident when somebody, if you released your car into to be used as a robo-taxi and an accident occurs, who's responsible? And he went, well, Tesla, I suppose. But it was strange that it was almost like he had to think about it, that he hadn't thought of the question before. I can't believe he didn't think of the question before, so I'm not entirely certain why he answered in that particular way. But if you're planning on becoming a robo-taxi, that's going to be front and foremost in your mind. It might be that he just didn't really want to be asked the question, because of course the concern then is, well, if you're going to be responsible, then do I want to invest in your company for the first few big lawsuits that are going to occur? Okay. One of the other interesting things was that with their current autopilot that they have, some of the audience were saying that they have problems merging in traffic, where the car goes to go into another lane, but in LA traffic, and it's the same in most cities, Dublin is quite similar, you're trying to move into another lane and the other cars don't let you, and you have to be quite aggressive in order to get yourself in there. That he said that there would be a user selectable setting in the near future where you could actually say, I want my car to be more aggressive, and that from that point of view, it would risk what he called a fender bender. I know they don't have fenders obviously on Teslas, and if you have a fender bender in a Tesla, it's going to be quite expensive because of all the sensors that are on the extremities. But the idea would be that in most cases, the only way for you to actually get from one lane into another is to take some level of risk that you're going to tip off another car. Not a serious accident, but a brush. So the idea is that the car autonomously would decide to be quite aggressive to get into another lane. I think that's quite new, and it's not something that I hear from other manufacturers and things like that. This idea that they would be aggressive in doing it. It's all to do with how are we going to deal with people that are going to bully these autonomous vehicles where they're going quite the other way. So this is all about setting the narrative as well for both regulators and for the public to expect, these things are going to bump into other cars. Yes, there's going to be accidents, but we're going to have far fewer accidents than the average human driver, and therefore for that reason we should adopt it purely for that reason. Okay. Now he had an idea that maybe it would need to be maybe 3 times as safe as the average human driver. Well, he didn't say average, he just said as a human driver. And of course, I'm assuming an average human driver rather than the best human driver with that. That maybe when it was 3 times as good, that regulators would allow it. But I heard figures at a conference that I was at last year that they expected the regulators would not allow it until it was 1,000 times as good as the average driver. Simply because of the fact that when you have an accident and people don't want to give over control, and so for the public to become accepting of it. So those are two very, very different figures, as you can imagine, 3 and 1,000. And I think that the thing here is that both sets are trying to maybe put down an anchor for other people, that it probably won't end up at either one of those figures, but that if Tesla are trying to say 3 times as good, the regulator might come back and say no, 10 times as good, rather than if they said 1,000 times as good, and the regulator would come back and say 2,000 times as good. So you can see how a lot of the rhetoric that's going on is not really to do with technology and is all to do with I don't want to call it politics, but this idea of getting the idea into people's heads. So it's about winning hearts and minds more than maybe specific to the technology. Can I just check that you're all still there, guys? That you can hear me there? You can, yeah. That's perfect. Okay. Because I have a second computer here, but I just want to make sure that you're all still seeing what I'm seeing. Okay, so they also give an autonomy timeline, a timeline for where they're going to be autonomous, and they said that they'll be feature complete autonomous, whatever exactly feature complete means, of course, and this is where the vagueness comes in, but that it would have the full ability to be autonomous by the end of this year. Okay, now that's very aggressive considering what the car can currently do. They can currently merge in lanes and things like that, and they can turn at crossings and so on. But they're saying that they will be able to fully do it by the end of this year, and that by the second quarter of next year, so roughly around about now or in the next month or two beyond that, that what they're saying is that they will be feature complete to the point that the driver does not need to pay attention. Okay, which is a significant jump beyond that. The point is, Fiacre, that this is the third part, which is feature complete autonomous with regulatory approval in some jurisdiction. Now that's not clear. What jurisdictions is he talking about? Who is going to allow it? And I think if you're going to have robo-taxis that are driving, and he's talking about the end of 2020, first robo-taxis with no one behind the wheel. Okay, so in other words, I hail it at my house and a car arrives with nobody behind the wheel to pick me up. Okay, subject to regulatory approval, and he's saying that will be by the end of next year in some jurisdiction. Now, again, this is far outside of my comfort zone to be talking about, well, regulations and where is that going to work. But, certainly within the European Union and places like Japan, which have, a very strong base of manufacturers of cars, there would be a lot of pressure put on regulators not to allow Tesla to get some competitive advantage there. So there's going to be an awful lot of politics played there, even if they were capable of doing it. Could it happen in maybe some of the states in the US, or maybe in what they call a geo-fenced area, so within a certain section of a city? And they said, by the way, that they do not mean a geo-fenced area here. They mean that this can go anywhere. Okay. Could they do that maybe in some of the states? That's possible. But I think if you're going to get regulatory approval, you're probably looking at a country that is not a democracy. Okay, so maybe some of the smaller companies, maybe countries in the Middle East, possibly something like that in maybe some area of China or something like that. I think that there's more of a possibility there where you have one or two individuals that are able to make a decision, rather than somebody that is immediately answerable at the ballot box. Okay, but again, this is a long way outside of my comfort zone. But you can understand that when you're hearing these things, you immediately see all the possible problems that could happen. So I certainly don't think we're going to see it on Irish roads by the end of next year. I would not be at all surprised if some jurisdiction somewhere in the world allowed them to do this. That doesn't really mean that it's fully autonomous everywhere. Okay, but they may allow them to do it, and it may be reasonably safe over a certain amount of within a certain range. One of the things they suggested was that the idea of trucks in a platoon with a driver in the front in the front truck and maybe 4 or 5 trucks behind that, all following that, that might be something that regulators would allow first. Okay. Again, I'm not so sure about that, because while okay, there is still a human that can deal with the situation, the other ones are just following in line with a load of trucks. 5 trucks can do an awful lot of damage if something goes wrong, and so he seems to think trucks will happen before cars. I'm not at all certain of that, but I'm sure he's thought about it more than I have. So the technical content of the day was that they, and this is the bit that I'm really more interested in, because I can be a little bit more sure on it. They come up with a new piece of hardware called the full self-driving computer, and they also looked at how Tesla's computer vision learns and works. And Maurice, you'll be familiar with Andrea Karpathy, so I'm sure you saw him on that. He heads up this, and obviously he's very well respected within the community. They also looked at the rest of the software stack, which there wasn't as much in there. These two were the two big ones. So this is the full self-driving computer that they showed, and you'll see there that there are 2 chips on board, right? So we've got one there and we've got one there. Okay, these are the same as each other, and what we have around them is you've got RAM chips here. Maybe just you've got RAM chips here, and here, very, very close to them for data, and you have the same for these ones as well, so they're equal there. And what they also have is they have these flash chips here for their for where the program is going to go. All their cameras are over here, so these are the camera inputs, and they have 8 cameras that they can attach up to these, and the 8 cameras are on the car. So even the cars that were built before this computer came out, and this computer only started going in the last month or so, it was meant to be backward compatible with the cars that were there. The idea was that they put more cameras on the cars than they were probably using, in order that they could upgrade the cars, but also that they were getting plenty of information from the cars as well. They've got 2 separate power supplies here and here. Now, I'm not sure what these are. I know that there should be a radar inputs, and there's also 12 ultrasonics. I'm not entirely certain where they come in the chip, but it's not vitally important for a discussion today. So one of the things about this chip was to do with redundancy, and the idea was that they have 2 fully independent computers on board. So those 2 chips are fully independent. The power supplies are independent of each other. So one power supply is for one chip and the other is for the other. Each boots independently with its own operating system. There's 8 camera inputs, and the idea is that if any part of the car, or any part can fail on this, and the car will be able to continue driving. So cameras can fail, a chip can fail, a power supply can fail, and the car can continue driving. So they claim, again, but without numbers, it's important to understand that probability of failure is an order of magnitude lower than human driver losing consciousness. And the reason I say there was no numbers mentioned is that there are numbers mentioned in other places, and those numbers are in some cases disputed. And so when you just hear an order of magnitude, which means roughly 8 to 12 or something like that, well, how is that all measured, and what are the numbers? There are 2 power supplies, as I said, one for each chip, and half the cameras are on one power supply and half the cameras are on the other. So you can see that they've it well separated out, that if anything fails, that they can continue going. But all 12 cameras all 8 cameras feed into each of the chips, and that means that all of the cameras can be looked at by any one of the chips and decisions made. They have 12 ultrasonic sensors, again, going to each of the chips, and they have a radar as well going to each of those chips. So all those decisions are made, can be made on one of the individual chips. They're actually made on both, and then there's a discussion had between them. So the pipeline is that each chip processes information independently. They then come up with a plan. So there's a plan output from this. So basically, there's a neural network on each that go through. There's actually many neural networks that go through in each of these chips. They formulate from that a plan as to what they should do. In other words, how much accelerator, what steering angle, whatever else, or how much brake or otherwise they need. And from that, there's 2 plans formed, one for each chip. There's then systems whereby that they compare their plans with each other, and if they agree, they act to drive the car. Now, exactly what happens when they don't agree, I'm not entirely certain, and we'll also see in a few minutes that sometimes that second chip is not necessarily being used in the same way So presumably one of them just goes with its own plan. But again, that wasn't entirely clear. If I was in the audience, I might have asked these questions, but of course I wasn't there. So I'm just going by the people that were in the audience. And then what they do is, after they execute the plan, they have mechanisms whereby they can read things in from inertial sensors and GPS and all sorts of things to say, well, okay, well, I made a plan. I told you to do this. Do the sensors suggest that we did do that? Okay, so there's a validation then on what was carried out. So that's the idea. The chip, just some of the technical detail. I don't get hugely excited about this sort of stuff, but so it's a ball grid array with a certain number of 2,116 balls on the bottom of it, and it's about 37.5 millimeters by 37.5 millimeters in size. So almost 4 centimeters by 4 centimeters. This is each of the chips that are on the boards. So this overall board, they said, is not that big, and it's capable. So if you can imagine that just one side here is 37.5 millimeters, you can get a sense of the rest of the size of the board. It fits behind the glove compartment, so it's not a huge computer that sits in the back of the car or anything like that. So it has 12 metal layers. It uses a 14 nanometer technology. And they were asked, well, why were you not using some of the newer technology? Maybe, I don't know, it's a 10 nanometer and there's 7. Some of you that maybe work in Intel probably know that a bit better than I do. They were asked about that, and they said that some of the IP that they wanted to buy for the chips were in 14 nanometers, so they completed the rest of it in 14 nanometer. It's 260 square millimeters in size, and just to give you an idea, this is the actual silicon area. A standard chip in a mobile phone would probably be about 100 square millimeters, whereas one of the big GPUs, the big powerful GPUs that you use for deep learning, they would normally be about 600 to 800 millimeters in size. So this is somewhere in between the two of those. It's 250 million gates, it's 6 billion transistors, and it was tested to AEC Q100 standard, which is a standard for testing hardware chips for automotive. Now each chip, sorry for the density of this slide, but each chip has a camera serial interface of 2.5 gigapixels per second. So that's a lot of pixels, but then again, there's a lot of cameras that you've got to take this information in from. So that's and this comes in a raw format for feeding into the neural networks. So I know that question got asked earlier in the module about which would it do. So we'll kind of get an idea about how they do it in this particular case. They have on-chip network for RAM, and it's 4,266 gigabits per second, which I think is pretty fast compared to most of what you get for a laptop or a computer. I think it's at the higher end. 68 gigabits per second. It's actually, that's gigabytes per second, I think, peak bandwidth. Image signal processor, which can do 1 gigapixel per second, and that's a 24-bit pipeline. So rather than 8-bit, this is 24-bit, and that's not necessarily just in terms of color. That could be in terms of high definition. So they've not high definition, high dynamic range is what I meant to say. So high dynamic range images will have a lot more than 8 bits associated with them. And they do advanced tone mapping, so that's if they want to bring them down into a smaller range like 8 bits or that, to decide how to bring each of the parts together. So a little bit like I showed you in the first lecture, where the sky is too bright and the ground is too dark, and so what you do is you bring the sky down to a darker value and the ground up to a brighter value, and they all kind of meet in the middle. So that's advanced tone mapping, and this is done in hardware, and then they have advanced noise reduction as well, which is obviously very important. They have 2 neural network processors, and this is probably the newest part. So while the GPUs can certainly do most of the things that neural networks want to do, these were built from the ground up to deal with neural networks, and there's 2 of them, and so we'll see more about that in the next slide. So this is a ground up neural network processor. They have a H265 video encoder. So remember, this stuff is coming in image by image in over 8 cameras in RAW format. And what they want to be able to do is to encode that, so be it into MPEG or whatever. So it's this particular encoder format, 265. And that's if you want to keep a recording of things that happened on the car. So for example, you want to use your cameras as a dash cam. Or if you want to just have clip logging, and we'll see later where they actually use that in order, when they see some sort of an anomaly, they take a recording of that, and that gets uploaded to the cloud where they can then look at that data and decide what did the car do wrong. So we're going to come back to how they use that in a few minutes. There is also a standard GPU, but it's not a particularly powerful one. 1 gigahertz, 600 gigaflops, and it can do floating point 32 and floating point 16. There are 12 ARM cores on the, so standard CPUs, the sort of ones that you'd find in mobile phones. There are 12 of them on the chip to do all the other sort of things that you might want to do on board for simpler sensors, simpler actuators, things like that, making decisions. There's a safety system, so there's a lockstep CPU, which I'm not that familiar with, but it's the idea that the two CPU, the two chips have to make a decision on their plans together, and therefore I think that helps them to make sure that they stay in step with each other and that they don't give conflicting commands. And then there's a final drive control and a control validation there. There's also security, which is that you can get yourself one of these things, but you can't write software for it unless it's been cryptographically signed by Tesla. So therefore, that protects from, in terms of cybersecurity, that the car cannot be hacked. Now, I'm sure people are working on a way to do it already. I'm sure if they can pretend that they're signed by Tesla, that might work. But again, it's not my area. We have other people that'll tell you more about cybersecurity. So there are two neural network processors on each chip. This is important. There's two of these on each chip, and then there's two chips on board. 32 megabytes of SRAM, 96 by 96 multiply add array. So any of you that are familiar with neural networks will be aware that the major calculations you have to do is you have to multiply two sets of numbers by each other, two matrices, and you've got to add up the result. So it's called multiply array, multiply add, or multiply accumulate. They're doing it as a full 96 by 96 array, which means you can do a huge amount of them in just one clock cycle. Now, lots of GPUs and DSPs have that sort of hardware, but what they pointed out was that when you do that really efficiently, you find that some of the other things are actually what slows you down. So what they did was the nonlinear activations that you have in neural networks, they put those in as hardware. Now the ReLU, which is the rectified linear unit, is the one that's used most often, but there are other ones like hyperbolic tangent and sigmoid and softmax and so on. Those apparently are on there as well. They were asked that question. They only mentioned ReLU as part of the hardware. Again, if you don't know what that is, don't worry about it, because we will be dealing with it more in the module that I'll be covering next year on machine learning. There's special pooling hardware. So pooling is used in neural networks, again, to resize your image down the way, and they have hardware for doing that rather than you doing that in software, again, to keep the speed up. They use a batch size of 1. Again, if you're familiar with neural networks, we often put a batch of images in together and make some update with regard to that. This is not doing updates. It's only looking at one image at a time. One of the things I'm a little unsure about here is that, as far as I can figure, the Tesla entirely works on one image at a time in terms of all of the predictions and so on that it does. It doesn't really do things on looking at 5 or 6 images in a video sequence to determine maybe something like optic flow and where things have gone. I'm not absolutely definite of that, but certainly in terms of their neural network, they seem to only take in one image at a time, make a decision based on that. And I don't know whether they can then be combined in some other way to tell you something further. I assume there is a little bit of that. But that is an interesting point to be aware of, particularly when you consider that there's so much that we know about vehicles from movement. Okay, so I thought that was quite interesting, and I'd like to know a little bit more about that. But that's as much as I know for the moment. 36 trillion operations per second at 2 gigahertz. Now, 36 trillion seems much a higher number than 2 billion, which is 2 gigahertz. But the point is that it's because of the fact that they can do this 96 by 96 multiplies and adds and then all these other things in one clock cycle that allows them to get such a high throughput here. There's 2 of these per chip, which allows you 72 tera operations per second in total. They had wanted, when they were designing this, to make sure that they had over 50, so they got up to 72, which is quite impressive. At different points, they mentioned 2100 and 2300 frames per second. I think 2300 is the one that they're kind of sticking with, but it was a little bit unclear on that. So 2300 frames per second sounds very fast, but you've got 8 cameras, remember, and if you've got 8 cameras going at maybe 60 frames per second, you can divide it in there yourself. You don't necessarily have that much headroom around it. So and for any expansion that you might get in the future. So this is the number of frames that can go through a neural network and have a decision made is what this is referring to here. And clearly, if we've got 8 cameras, we want them, each one of those, to go through a neural network. They all go through them separately and so on. So it's that many frames per second is what we have to deal with. Okay, so it sounds very high, and it is, but it is important to understand why that's required. Now, this is one of the important things that they mentioned, but when asked the question, he was asked the question about, could you use the big array of these that you have in vehicles? Could you use that as some sort of a network for training? So in other words, when the people are asleep and the car is there and it's plugged in, could you actually use that as a huge supercomputer? And he said, well, it's an inference optimized chip. And I'm not sure whether the person who asked the question really understood that, because I had already understood it before the question got asked. So I assume the questioner had misunderstood something about the chip. But it is maybe something to make very clear here. Again, as I say, we'll be talking more about neural networks next year in machine learning. But one thing to be aware of so just before it crashed there, I was talking about this being an inference optimized piece of hardware. So I just wanted to explain a little bit about neural networks for anyone that isn't familiar with them. And when it comes to training, what happens with the neural network is we put inputs in, it goes through each of these layers and makes different calculations as it goes. And it comes out with a prediction, and we check that prediction against ground truth. And there are different complex cost functions that we use in order to determine how far away from the ground truth, or from what we would like the prediction to be. Okay, so this is when we're doing supervised learning or training of a neural network. And the difference that we have there, what we do is we try and get the derivative. All right, so differentiation is what we're dealing with here. We try and get the derivative of every parameter in the system. So each one of these and each one of these is each of these are parameters. More these values in between that they get multiplied by. But again, as I say, I'll explain that in more detail in machine learning. So we need to update those values, and we update those by getting the derivative of those values with respect to the loss or the cost that we have here. And because this entire network is just a mathematical function in each different way, we can do this by differentiation using the chain rule and work all the way back. The thing is that it's quite expensive. So there's an algorithm called back propagation, which is a mechanism to get your values, your derivatives back through the network in a fairly efficient manner. It's an old algorithm, but when new hardware came along, it was something that really worked very well. Now, the thing is that the back propagation algorithm, one of the things it requires is for you to retain each of the values that you had coming out at each different point. Okay? And remember that we've often got maybe, some of these have 150 layers, some of these networks, not all of them, but they'll have a lot of layers, and they might have millions of these activations. And because of all those values having to be stored so that we can then work back and calculate how much we need to change our weights by, we need to have a lot of memory that keeps everything together. And it means that every layer has to continue to keep its value until it's gone all the way through the network, given a prediction, and then learned all its way back. Now, what that means for things like a GPU is that a GPU needs a huge amount of memory, and it relies. It also has to keep in mind all the speed that it's going to take in order to get something passed. Now, when you fully trained one of these networks, all you need to do then is put an image in, and out comes a prediction the other side after it goes through all the layers. But we don't need to retain anything along the way. And that's what this piece of hardware is. It's very quick at doing that, but it would be no good at training because it doesn't have the memory. And in fact, it doesn't even keep all of the network in memory or anything like that. What it does is it really only keeps about a single layer at a time. It reads in a layer of weights, and it reads in a layer of value activations. It makes a calculation, and then it dumps those, and it works on the next layer because it no longer needs to keep that information there. Okay. Now, if it didn't dump those and it was able to keep a bigger one, you could actually have a pipeline of images coming through. So a little bit like they use in a lot of chips in order to speed them up. We have this pipeline idea where when one piece of hardware has been used, the other one is used in a different part of the chip. But in this case, I think what they do is they simply have a layer at a time as they go through it, and then they do this for each of these. And so it's very, very quick at just grabbing that data and doing a calculation and then dumping it and moving on. And the whole idea is that you keep your memory very, very close beside you. So when we talk about how good this piece of hardware is, you need to understand that it would be no good for actually training a neural network. It is all about getting a very quick value out of it once it's been trained. So training doesn't happen on the car. Training happens elsewhere with powerful computers, and then it's then sent to the car. So that's how they can also do a lot of this for very cheap in terms of energy usage. So this is this is important to note that the full self-driving computer is for inference only. It is not useful for training neural networks, and Pete Bannon, the chief engineer, had a single customer to deal with. So unlike NVIDIA, who have loads of customers, be it for gaming, or be it for self-driving, or be it for neural networks being used somewhere else, or machine learning, Tesla, there was only one customer in this case, which was Tesla, and it had a single purpose, which was self-driving, and you can develop it entirely for that. So that is where this is particularly good. Now, NVIDIA also develop chips for self-driving, but they have to develop it in such a way that it's useful for all of the community and for what they might want, and that therefore they're at a slight disadvantage there. Tesla tried to play upon this idea as well, that that's why they might be better. Okay. So this chip had a very small instruction set. So this is basically an ASIC, just a single use chip. Okay. Sorry, application specific integrated circuit is what I meant to say. Okay, so it has a very small instruction set, just a DMA read. So read in, that's direct memory addressing there. So read in a full load of memory, write a full load of memory, do a convolution, do a deconvolution. Again, we'll worry about that when we get to machine learning as to what exactly that is. But it's generally we would use it for upscaling. Do an inner product, which again, just these matrices. Do some sort of scaling. Do an element-wise something to an individual element of something, and stop. Okay, I'm not sure where the stop comes into it exactly, but because most embedded systems just run until the power gets cut, but presumably they have a stop for some reason. So the compute, multiply, add in a single cycle of this chip, what they can do is they can read all the activation is read from, I don't know what I was trying to write there. Ignore that word. Okay, so all of the activation data is read from memory. The weight data is read in the same clock cycle, and then 96 by 96 multiplies and additions are done. That's 9,216 of them, and that's every clock cycle, and they do 2 billion of those per second. So you can see how there's an enormous throughput in what they're actually doing here. But again, GPUs could do this as well, except for the fact that what they're really doing is they're optimized for training as well. They also compile the neural network. So when the neural network is developed on one system and you've got your weights, what they do is they compile that, which means that they're going to be doing quantization of weights and things like that. So where the weights might, coming from your powerful training computer, might be of a certain resolution, they're going to cut that resolution to some extent. So they're going to do different quantization and things like that in order to have it quickly used on the chip. So I think they use a lot of integer multiplication and so on, rather than using floating point in this neural network hardware. And so the program is resident in SRAM, running a network takes just 4 stores. You set an input buffer address, you set an output buffer address, you set a weight buffer address, and the program address and run control, and that does each job for you. So some of the results from it. So firstly, one of the things that was vitally important to them was that they needed this to be backward compatible with the cars they've already designed, and that meant that they couldn't go above 100 watts. Now, the previous system used 57 watts. They did go above that, but they couldn't go above 100 watts. And this was one of the things they had to keep with. They managed to get it in at 72 watts, which is very impressive. Objectively, this is extremely impressive. The neural network accelerator that's in it only uses 15 watts. So you can see that there's probably some level of improvement there to have taken so much energy usage in terms of the neural network and its other parts where they can probably make benefits. In terms of their previous hardware, which I think was developed by NVIDIA, they can do 2300 frames per second, whereas the previous hardware that was in their cars up until a few months ago could only do 110. So clearly that was only for use in terms of, you know, lane keeping and a few things like that. This goes beyond that, and they reckon that this is enough to do full self-driving. So this is a 21 times improvement, which, you know, they kind of said, well, you know, 2 or 3 times improvement, that's the norm. 21 times is absolutely huge. But then again, this is their first development of a chip. They did obviously get this guy Pete Bannon has 35 years experience in this area developing chips for Apple and people like that. So they got in the top people to do this. It was a major improvement, but again, it's because it was developed for one customer and one specific use. So the full self-driving computer can do 144 trillion operations per second. Now, this is one of the contentious parts, because they said the NVIDIA Drive Xavier that they compared it with, which is NVIDIA's product for self-driving, only does 21 teraops. So this was maybe a 7 times improvement on it there. Now, NVIDIA say that it's actually that particular product is 30 teraops, which is not an insignificant difference. But the second thing NVIDIA say is that product is not meant for full self-driving. That's for kind of level 2 lane keeping ADAS sort of thing. And that NVIDIA have a system called Pegasus, which actually is 16 cameras rather than 8. It manages 320 teraops. What NVIDIA don't probably say when they shout this back at them is that, but actually it uses 500 watts. And of course, Tesla can quite easily come back and say, well, no, we're comparing it with the under 100 watts, which is what we could use in our car, and therefore for a like for like. So I think it is, when you look at this, what Tesla have achieved here is that they are getting basically 2 teraops per watt, which does seem to be better than anything we've seen before in this particular space. But do bear in mind that Pegasus from NVIDIA came out in 2017, in October 2017, which is almost 18 months ago now. So you can presume that there's a lot in the pipeline there with NVIDIA, and NVIDIA, they are really top people when it comes to this specific thing of high performance computing. So I think it would be wrong to rule out NVIDIA's products here, but obviously Tesla want people to invest in them and to say that NVIDIA are a great company, and they did pay them that compliment, but it was kind of an underhand compliment in saying, yeah, but NVIDIA have to develop for all these other people, and we're just developing for ourselves. So I think all we can say is watch that space. I can assume that if NVIDIA can manage 320 teraops per second, they can also manage to bring that down in terms of energy usage. The one that did 30 teraops only used 30 watts, and actually there was a question at the thing about they said that they thought that they were using less power than NVIDIA, but they weren't for that particular one as well. Okay, so there's a lot to come there, but nonetheless, this is a very impressive chip, and I don't kind of want to say that that's not the case here. It's just that it's maybe not as clear cut as we think, as we might think. They're not that far ahead. They talked about where they were going next with their hardware, their next hardware update. So they're about 18 months into that cycle. That previous chip, that board, that took 3 years to develop, and that was considered quite quick. They're 18 months into this, their current one, and they reckon about another maybe 18 months to 2 years to go. The current FSD is already in vehicles. This one is maybe 2 years away. They were asked, well, what's the major step forward that's going to be in your next chip? Now, Pete Bannon, he whispers the word safety, but Elon doesn't really pick up on it. And Elon says, look, it'll be 3 times. He actually didn't say as fast, and he just said 3 times better. You just said 3 times better than this chip that's here, and that he was basically saying that because the others are behind, in 2 years' time we're going to be 3 times better than this. They'll only have caught up with where we are now. But it was interesting that Bannon said safety, and then they didn't pick up on it again. Now that tells you that he's the guy designing the chip, so clearly safety is a major thing that's coming, and something that Tesla, when they get there, will probably try to say we're safer than everybody else. So it's clearly a big thing that's important, I think, to all the manufacturers. But the second thing is, the reason you don't want to say that your next chip you're working on safety is because it suggests that the current chip is not safe. Now, that's not the case. You're always trying to make improvements. You're always trying to make things safer. It doesn't mean, cars without seatbelts, it wasn't that they weren't safe. They could be driven safely, but they got much safer when we put seatbelts into them. So we're always trying to get to become safer. But clearly you don't like to say that word because it then suggests what you currently have is not safe. But it is interesting to see where, that's probably the key thing that they are concerned with. I don't know whether they meant to say it or not, but that's certainly what was said. You don't know what if this is choreographed either, so it's hard to know. So this moves us on to Andrej Karpathy's part in this. And he came on to talk about the whole neural network side of things and what they did. One of the things they showed, and I thought, I kind of feel this is almost poorly chosen to show, they were trying to show all the places where they have cars regularly. And you can see that you've kind of got San Francisco and California over here. You've got the whole kind of New York area going down as far as kind of Washington, D.C. and so on. They're obviously very heavily utilized. And you've got Europe here, and I think somebody's driven into Sligo there by the looks of that. I'm going to assume somebody's driven into Sligo by the looks of it, and somebody's even driven into Donegal. So I'm sure Shane will be delighted as well. Mayo's not doing so well. Okay. The thing that this does show, though, it really does show the haves and the have-nots. I mean, just look at that section where there's absolutely nothing coming in. Okay. Yeah, and I've seen a few around Sligo as well. So presumably they are all leading back into them. Okay, so but it is interesting to just show that really, when you talk about self-driving cars and where it's going to go, that there's a whole big part of the world. I mean, India there. Lot of driving in India is going to be a big challenge, as is the west of Ireland. Of course, is obviously a big challenge with the weather, if not just the roads. But there's clearly a whole thing there. So Colin was asking about Norway. Now I think Norway, it's unusual to see that it's gone so far up into Lapland, whereas you're not seeing that in Canada. And I think that is to do with the fact that Norway have special incentives for buying electric vehicles, and I think you see the result of that. So I think that's also very interesting as well. That Norway, more than Sweden or the rest of them, you can see that there's obviously clearly some major roads going across Sweden that are used, but it is very interesting just how much of it is used in Norway. It's interesting to see that. So this is the fleet that they're saying is out there. So Fiacre has come up with some figures there. 50,000 electric vehicles already in Norway, and they're a small population. I think Norway is similar to Ireland, is it, in terms of size? About 5 or 6 million. I was off the impression, but I could be wrong with that. So that's very high penetration for electric vehicles. So we assume that is to do with incentives. So this is the idea of the fleet, and the fleet of cars. They can get information from those fleets as soon as they're attached to the internet, and therefore they can utilize that. Whereas Waymo and so on, with Waymo and so on, that they're all using their own cars, and therefore that limits the size of their fleet. And Maurice, yeah, I think there's just what is that? Is that Abu Dhabi there, or where is that? That's on the edge there. I'm not sure where it is. The rest of the Middle East does seem to be fairly dark. Which I was a little bit surprised at. I think that's Israel there, but I'm not sure where that is. I have a feeling that's Abu Dhabi or some of them. I think is just on the edge there. Okay, so let's have a look at this. So this is the neural network essentials and how they went about it. Well, the first thing, Andrej Karpathy would make the point, and I wouldn't disagree with any of this, is that to train neural networks well, you need firstly a very large data set. But the second thing is you need a very data set within the things that you want to train for. Now, obviously, if you're training something to tell between the difference between dogs and cats, pictures of cars is not a good variation to have in there. But if you're training between dogs and cats, you need to see every different type of dog and cat and in every sort of configuration that you want. So in terms of autonomous driving, you obviously need to see every sort of thing that you're likely to see on the road for the area that's going to have to be operating in. So varied is important. And this is the point they make. You need a real data set, not a simulation. Now, there's lots of the companies have simulators, including Tesla, and where Tesla might be able to do, a million miles or a billion miles, the other ones can do 1 trillion miles on these simulators. But the point that Elon makes is that simulation is like correcting your own homework. If you're only testing for what you're able to do, you're not testing for things that you don't already know about. Now, I did think it was a funny statement because, of course, this entire exercise that we watched was Tesla marking their own homework. Because they were saying how brilliant they were, but of course, it's really up to maybe the rest of us to decide how brilliant they are, rather than just them themselves. They can, of course, give over their point. Okay. Yeah, Colin, I don't know, but presumably, so Colin was asking about the left-hand drive and the right-hand drive in the European Union, and in others. I mean, it's in Australia as well. It's in a lot of countries. The right-hand drive. Presumably, they have to keep those separate because they're very different sets of rules. But there are also different sets of rules in the different countries as well. They did not go into any detail on how they handled that. It never got mentioned. So unfortunately, I don't have any clear answer to you as regards whether this would work, but only in a left-hand drive country. At first, and then it would take a while to move over. I don't know, but I'm fairly certain that the cars are available in both, and it's just a matter of what side of the road they're on. But it would have to have different neural networks for each one. So they refer to this thing as the long tail, and this comes up a lot. If that guy, I've forgotten his first name, is it Taleb, who wrote the book about the black swan, which is all to do with with the financial crashes and so on, which are unlikely events do happen. And when unlikely events happen, they can either happen in two ways. They can happen in a way that they happen, but they're of no particular significance, or they can happen and they can be a major catastrophe. So if they happen and they're of no particular significance, that's no big deal. But if they happen and they're catastrophic, it really, the fact that they happen quite rarely doesn't matter. It's that if they happen at all, we're in trouble. So this is not the design of the slide. I want to make you aware that this section that goes here, this section here that you're seeing there, that is a diagram of the distribution of data is what they're trying to show there. So don't just think that that's just some nice colorful background. This isn't like a Gaussian distribution. This is more like a Poisson distribution, which is distribution of how likely things are to happen over a certain amount of time. And so what they're trying to say is that, the standard way of driving, that happens 90% of the time. And then every now and then you've got like a pickup truck with a load of stuff in the back of it. And that's an unusual thing, but you need to recognize it as a car. That gets you up to 99% of the time. And then you've got the situations where there's bicycles on the back. That's 99.9% of the time. Then this situation here, it's hard to see it, but the car is actually sitting on the back of a low loader. And you need to be able to tell that is just one vehicle there and it's not two of them. And then you've got the very unusual cases like a car that's on its side or a car that's airborne. Okay. And what they're trying to say is that if you don't have access to these very unusual situations, then you can't train the neural network. And they're saying that with their fleet, they do get access to all of these. Now, at first, this seems, well, yes, that's fine, but what are you going to do? Collect just billions and billions and billions of images until you get the unusual things happening? But that's not how they do it. So it is quite interesting to see the mechanism that they go about to try and get this information. So here's the pipeline of how they do it. So what they do is they train a neural network first. Okay, so that's them training their neural network there first. So here's their neural network that they've trained, and when they've trained it, they put it down onto the car. The car then has to have some mechanism to say when something didn't work properly. Okay, so some trigger. They didn't tell us necessarily what the triggers are, but the triggers could be things like they make a prediction. Okay, but that prediction doesn't pan out. They make a prediction, but the driver does something different. So either the driver is in this autopilot mode and the driver is so panicky that they take over from the car, or it could be a situation whereby they're not in autopilot mode. They're just driving the car, but this is still operating. It's still making predictions. And then when the driver does something different, it goes, oh, that's not what I was expecting. Now, it might be that the driver does something different, but they had a 20% probability on that happening. That's okay. But it's when the driver does something entirely different or something entirely different happens, the tiny less than 1% of the time, then what they do is they take a recording of that via that mechanism that we talked earlier, where they do an encoding of the video. And the next time they have an opportunity, they upload that to Tesla. Now they take a recording of the last number of frames as well, so that they see what's leading up to it. Tesla then get that, and either by human annotation or by some automated annotation, what they do is they go and annotate that to say, okay, this is what actually happened next, so that the computer can then learn from that scenario. So this is to pick up unusual scenarios so that they get a different view on the world. The other thing that they can do is when they see something unusual happen. So let's say, for example, they see this. Okay, so this is supposedly a rare event. What they see is they see a bicycle and they see a car. And really, what a human sees here is a car with a bicycle on the back. They don't need to worry about the bicycle. There's nobody on it. It's not cycling anywhere. So therefore, we would be better off just having this as this is just a car. So what do? They get one of these and they see something unusual. And what they then say is they set a trigger in all of the cars or in many of the cars and say, okay, I want you to look out for a situation where you have a bounding box over a car and a bounding box over a bicycle, and those two bounding boxes are very largely overlapped to some amount. Find me examples of that, keep me the recording of it, so that then goes into our system, so we can go out and actually get more of these unusual cases by asking the fleet for them, so to look out for them specifically. So it mightn't be that anybody made any unusual movements with regard to this, but it might be that because somebody did, they then go and ask the fleet for all sorts of situations in which this happened. What they then do is they then label those, so the humans go and label them, or some other mechanism labels them, and they go and train again. Now here's what's interesting. They send that neural network out, but because the system has two chips on it, they work in a shadow mode. So one of the chips works as the standard neural network that was there up until now, that's been released. And the other one is the neural network that's trying to be trained to be better. And what it does is that they both put out predictions. And when those predictions disagree, then what they're going to do is they're going to take a recording of that, send it back through the system, and test it again, or learn again and learn again. Now, one of the things that can go wrong, going back to this problem, is that if we take lots of examples from over here, then what we do is we actually give the neural network a false sense that these happen more often than we expect. So let's say you're driving along and there's a car in another lane and it suddenly cuts in front of you. Okay, so that's an unusual thing and you weren't expecting it, and you keep a recording of it. But now what you do is you train the network to expect that every time there's a car in the other lane, it's suddenly going to cut in front of me. And of course, that's not what it is. So the danger is that you create a really nervous autonomous vehicle that thinks that the world is out to get it. So what they need to do then is that they need to constantly say, have this go into the system. The system predicts that car is going to come in front of me, or that car is going to do X, Y, or Z. I need to be wary of that. And then it doesn't happen. And so what they do is they take a recording of that, annotate that and say, now look, it didn't happen. But they still have their few examples of when it did. And when they get this all to a situation where they have the right ratio of false positives and false negatives occurring and that they're happy with it, they then deploy that as being the main neural network that runs from then on in. Okay, so that's the idea. And they're saying that they have a huge advantage over other manufacturers because they can't go out and ask their fleet for this information. I'm not sure that's absolutely true, but if the hardware doesn't have all the self-driving on it, all the self-driving hardware on it, then there is a good chance that other manufacturers cannot go and grab this information when they want it. So there's a lot that they have designed into the cars to allow them to get the right information to then train their neural networks for 2 years down the line. Okay, and that's the way that they've gone about it. How well it works? Well, they said it works very well. That's to be decided. So when they see something like this, they go out and ask for loads of other examples. You can see there, loads of other examples of these. You can see that one, the bike is kind of hanging a little bit funny on it and so on. So these are all different mechanisms that they have for getting other images so that they can train further. And they put it into this thing, as I say, called shadow mode. So when a new version of the neural network has been trained, it's released to the car, but in shadow mode. This means that it goes on one of the two chips and makes predictions. The other side then is imitation learning. So imitation learning is where you make a prediction, but the human driver does something differently, and you're learning from the driver. You're learning to imitate the driver. Now, clearly, there's a danger here with any of these. Are you imitating a bad driver? Did the driver take over from the autopilot because they were just nervous, but the autopilot was doing fine. Okay, so what we normally call a backseat driver. So presumably what they also know is they know a fair bit about the driving habits, and they have statistically figured out what drivers it's good to take information from and what drivers it's bad to take information from. In other words, drivers that get themselves into trouble, you don't want to take their information. And again, you can do this by looking at the statistics, and if you have a powerful chip that can make enough of those decisions, the chip on the card doesn't do any training, but what it does do is it says, I need to be trained on this. I've spotted that something's wrong. So if the predictions turn out to be wrong, then they're recorded, sent back to Tesla for review, annotation, retraining, and redeployment. And when false negatives and false positives reach a ratio that they're happy with, then the network comes out of shadow mode and into full mode. Now, what's not entirely clear, because on one side they're saying we have these two chips for redundancy, and on the other side they're saying, well, one of the chips works as a shadow mode. And now if it's in shadow mode, is it a separate bit of redundancy or not? It probably is in most cases, but in the ones where it doesn't, where it gets something different, then there's a problem. So they're using the two chip idea in two different ways there, which, because they said it at different parts of the presentation, that might not be obvious to everybody, but I think it is important to kind of keep in mind with regard to that. Okay. So obviously they said the whole idea about LIDAR, and the main thing for LIDAR is able to tell you the distance to something. Now we know, as we've gone through our module, that there are other ways of telling depth, and we do that in classical computer vision, which is what we've covered mainly in this module. And that's what you can come up with there if you use classical computer vision. They wouldn't necessarily do that on the vehicle. They might do that, for Tesla I'm talking about, they may do that back at base, where they've got loads of images, and what they can do is they can actually build up slowly, not in real time, a 3D version of the world. And they can then use that classical computer vision to annotate the original images. So from a single image, we can now say that point there and that point there, they are certain distances away. Now, the idea here is that they want systems to be able to learn to predict from a single image, so from a monocular image, or perhaps for stereo images maybe in the future, to predict what the distance is to different items in the thing. And they showed examples of this, and you can look them up on YouTube. Cars are driving along, and they're making a prediction of how many meters away those cars are. So you can do that with classical computer vision if you do enough processing. You can also use sensor supervision. So LIDAR and radar can be used to determine the distance to something. And from that, what you can then do is you can then use that as the labeling for your images, and then get the images to learn, you get a neural network to learn what the distance they think it is from a single image. Okay, now that's only as good as we are, but we have lots of cues that we have for telling what distance something is away. Of course, we can be confused and we can get it wrong, and so can cameras. But it is interesting that this is how Tesla see it, that it is better for us to have a neural network predict the distance to something than to use LIDAR. Okay. The other one then, this is very much an entirely a deep learning idea. Looking at a video of movement. Okay, so I've got a video of movement here, and what it does is it tries to predict what the distance is of the moving objects, or of the different objects in the scene. And in order to get that right, basically what it has to do is it has to predict the correct value for all of the images to be consistent. Okay, so when it learns to get the prediction right in each different case, it can only do that by learning the correct prediction. So that's a mechanism that doesn't use any labeling at all. Now, the whole reason that they're talking about this is that the last thing you want to do, if you want to train a neural network to determine from individual images how far something is away, you do not want a human labeling it. It's going to take you ages, and secondly, the human has no idea from the image how far something is away. So you want all these other mechanisms to be used, and that's what they're trying to do. And they figure that that is the better way to go. Learn your way out of the structure problem, rather than to use LIDAR to figure out how far something is away. Okay, so and they learn full depth, so full 3D depth, full 3D path prediction in front of them. So the entire problem that we looked at in the last module, they're trying to learn that with a neural network just by looking at individual images. It has all the problems that we're aware of with regard to that, but it is quite interesting that, so this is very much like somebody driving with just one eye. Okay, and still being able to tell quite a bit about the road. And humans can drive pretty well with just one eye, so that's not unreasonable. Can we massively improve on the human driver if we've only got that? That's unsure. And then, of course, they make the point that you've got a lot of overlap of these different images and so on. So you've if each of the cameras come to the same prediction, then you're pretty sure that all the cameras have got it wrong, or that the prediction is pretty good. Okay. They do have a forward-facing radar, and they felt that that was adequate because that's the only direction that they're moving at speed. Now, I would have some. They were asked about cross-traffic at a junction, and I wasn't particularly happy with the answer that they gave. So, firstly, with regard to radar, as I'm sure you're aware from your sensor fusion and so on that you did with Shane. Radar can penetrate fog and things like that, so it's good for things that are occlusion, whereas things like LIDAR can't. So that's why they've gone for radar, but it has other issues. You kind of need objects to be of a certain size before radar is really going to pick it up and so on. Now, with regard to, okay, you're only traveling that fast in the forward direction, but when you're coming out of a junction, you've got things coming at very fast rate from the sides. And the difficulty there is that if you look back at this is like, something coming in this direction here, and your camera's picking them up. Now, really what's going to pick them up there is the wide-angle cameras. And the problem there is that these wide-angle cameras, they're tiny little cameras. The number of actual photons that come from a distant object and manage to hit that tiny little area of the camera lens is actually relatively small. And so, if you have a fast-moving motorbike, the number of photons even to just pick it up is quite low. And until it's almost right on top of you, you're not going to see a significant number of pixels that would allow a neural network from a single image to be able to tell that there's something there. Now, of course, in multiple images, you might see that there's some dot moving, but they did seem to suggest that they were doing this prediction on individual images and not doing it on moving images, which, again, I'm not sure if that was just me misunderstanding it or what, but I have some concerns around that you could achieve this. Now, he did say, well, the human viewer, all they have like a camera on a slow gimbal, okay, because that's your head. When your head moves slowly, it's like a camera on a slow gimbal because, of course, they can move much faster. And they said, they can see 360 degrees around the car. But the thing is that as a human, if I turn my head to look at traffic coming from the right or from the left, I'm now putting both eyes on it. And the second thing is I'm fixating on something in the distance. When I fixate on it, that then brings whatever that is onto the fovea of my eye. And the fovea of my eye is much higher resolution than the individual resolution of any particular camera that you're going to have. It can see some very, very good detail, certainly better than any of these are going to see. So generally speaking, when you're fixating on something, like you're reading a book, that section that's very, very high resolution is only the size of a single letter. Okay, so it's very, very small, but that's what we do. And so humans are actually not too bad at that because they can bring it into very high resolution. He made the point, well, we can see 360 degrees around the car, and we're actually up at a higher level than the driver, so we can see a much better view. All of those things are true. I'm just not sure they've got the resolution to be able to see something coming at speed. And anybody will tell you, the one thing drivers do really badly is seeing things like cyclists and motorbikes, things that are small but move fast. Humans are not good at it. And it doesn't matter how many advertisements that they put out in the television telling us to be more careful. We're just not optimized for that. I'm not certain these cameras are either, and that gives me some pause for concern. I assume that LIDAR can give us some little bit of an extra on that you would get a reflection back from it. The other thing that they were asked about was this idea that, in the snow, there's the idea of having a ground penetrating radar, which could see below the snow and determine where the road is. And they said, well, those things are not particularly useful. If you have an image of a snowy scene on a road, and you ask a human to say, where would you drive within this scene? They're able to actually annotate that and say, here's where I would drive. So they call this drive space. Okay, so where the drivable space, where can you drive within the scene? Not so much where the lane markings, you don't really need to know that. You need to know where is it safe to drive within the scene. Because even if you've lane markings, you don't want to drive right on top of one of the lane markings and have the driver the other side doing exactly the same thing. So this idea of drivable space was something that they brought up. And what they said is that if a human can annotate what it looks like in snow to say where to drive, then a driver can also drive, or then an autonomous vehicle can also learn to drive in that scenario. And that's more or less what they're saying, and that they actually drive pretty well in the snow is what they're saying. Okay. Some of the achievements of their autopilot system that they claimed, firstly, that they've done more than 70 million miles traveled on autopilot. That's impressive. It's far more than any human has ever traveled, but do be aware that most of the autopilot miles are not done, in people's driveways and, pulling out of junctions and things like that. They're done on the motorway. So that's not the same as having 70 million miles of, like a driver having 70 million miles. So when we talk about the number of accidents per million miles and so on, or the number of accidents that you have before you have a fatal accident, which I think is in around the 30 million miles or something like that. I think there have been some fatal accidents using autopilot, but I think there's only been maybe 2 or 3. And as you've learned from your statistics subject, statistics don't work well on 2s and 3s. Okay, you don't have enough numbers there really to work from. So therefore, it's difficult really to say, to kind of draw any conclusions from that yet. They've introduced automated lane changing only in the past few months, and what they're saying is that they're achieving over 100,000 automated lane changes every day on the highway. Now that is quite impressive, because lane changing can be quite difficult, particularly when you go to change lane and so does another car, and there's all the confusion and so on that happens. There's quite a little dance that goes on there. And they're saying that you really have to learn that. You can't really just program an algorithm or otherwise from it. So that is quite impressive, 100,000 automated lane changes every day without an accident. So there has been no accidents with that particular system yet. Okay, but we may see some in the future. Hopefully we don't. So in summary, Tesla have developed an impressive ASIC for self-driving. There's no two ways about that. They believe computer vision and deep learning is the main problem to solve, and are uninterested in LIDAR and HD mapping and things like that. Other companies still are. It's not something we can ignore. We can't suddenly say, well, Tesla said so, so therefore. But I think it is quite interesting. I think it will set the scene. These are a major player nonetheless. They use radar front facing. They use ultrasonics. So they have 12 ultrasonics around it, and they do use that for even close maneuvers on the highway, because other cars are within the range of those ultrasonics, and they can use that for predicting the distance that things are away and so on. They have advantages in the access to real image data. I think that's quite clear from what they have. And they have advantages in access to real motorist imitation learning, because most of the other companies, you maybe have a particular test driver behind the wheel, whereas Tesla have nearly 500,000 real drivers acting like real drivers, not having any special skills and doing all the things, and not being aware that they're really being monitored, and therefore driving as an actual motorist would drive. Of course, the more that they automate, the less that they're going to get from the human driver there. The one thing to say, though, is that in any groundbreaking area like we're in here, making predictions is very difficult. If you look at the kind of the rhetoric that's going on online at the moment, you've got the people who are dyed in the wars, Tesla and Elon Musk fans. On the other side, you've got people who are maybe working for other companies, or just don't like Elon Musk because he's a particular character that can polarize people. The thing is, though, that simply because Elon Musk in the past has managed to land rockets, and most of NASA and a lot of other people have said, no, you're never going to manage that, and has achieved quite a number of things, and there's no doubt he has been a net contributor to society. Simply based on those does not tell us that in this particular area that's going to work. That's not how groundbreaking areas work, that just because you have managed to keep your promises within certain deadlines or whatever it might be, does not tell us that will happen again. Unfortunately, I really I really would love if what they're saying with those very aggressive deadlines that are timelines, that we would have robo taxis on the roads, that I could hail one next year. I really would hope that I would love if that were true. But I think we it's very difficult to make those predictions, particularly that they would be ready to go, and particularly where regulators are involved. These things are very easy to get out of too. You know, saying that you're going to be feature complete. You can always say, look, my car can drive fully autonomously. If it hasn't really been tested in a scenario where a regulator has allowed it, and they can say, well, no regulator allowed this, that's outside of their control, they can still say that they met their promise. That's one of the things that makes me a little bit uncomfortable about these predictions. I tend to just work on data, so I believe it when I see it and it's working. I don't work on faith or on the reputations of people or anything like that, because that's not how science works. But nonetheless, I'm quite excited by this. I think it is interesting that they've kind of made this suggestion. I think it does put other manufacturers. It opens up the whole discussion about it. So I think it's no harm, even if a lot of people are saying what they're talking about here is a pipe dream. I still do hope that lots of people invest in this, because if people do invest, it will move on, and it's obviously good for us. And obviously, I like everything that he said about computer vision, because that suits me. It's my particular skill set. But nonetheless, I would not jump to the conclusion that LIDAR and HD mapping and those other things are not going to happen. What didn't get mentioned that I was surprised about was there was no mention of vehicle-to-X communication, connected vehicles, anything like that. So the thing is here that I would imagine that if had anybody brought this up again, they would have said, no, we don't need vehicles connected, we don't need all these other things. But that said, when we want to get to that society where we don't need traffic lights and we don't need all those other things, this is where we would need to go. At the moment, they're saying that the entire infrastructure is built for human vision, therefore that's what we should be using. I'd like to see a situation where, you could drive down the road and there were no road signs. I think it's a bit of a utopian future, but no road markings, no road signs. I think that would look much prettier rather than the environment that we currently have with these gigantic signs that we can see from miles away, traffic lights and so on, and have systems whereby that these cars can automatically interact with each other. The biggest concern I have, and this is why I want to end on this, is that from a computer vision point of view, image quality and sensor quality is something that did not get mentioned at all. They started from the point that they already have their image. And the truth is, when it comes to these cameras, these are tiny cameras. They're almost like pinhole cameras. The image quality in them is not superb. There's a reason why photographers use large lenses with their cameras in order to get good quality. There are fundamental limitations of these things, the number of photons that they can receive, the quality of the lenses. And you're working on a project there to do with calibration and so on. There's so much of that got absolutely no mention here, and that is such an important area that's the thing that more than anything gives me pause for thought. It's not that the question about whether LIDAR is useful or not or otherwise. It's, I know about cameras, I know about their quality. I'm not sure they can achieve all of the things that they're claiming they can do. There's no doubt about the fact that because they're at such low cost, they're a technology that's probably ahead of all the other technologies, and that if you put the money into them, they can, of course, improve. There are fundamental limitations, though, and I have concerns around that. And of course, the other thing is that obviously, because of the fact that if you were forced to use only one sensor, it would be cameras you would use. But I just don't think that they can get away with just that in order to do it. Clearly, humans do get away with it right now, but we're trying to replace human drivers. They're not good enough. So just replacing it with things that human drivers also have, I don't think that's going to quite get there. Okay, so that's all I have, guys. I don't know whether you have opinions yourselves or not. Whether any of you, I know Maurice watched it. I think we have a few more in. I think only Olivia's watched it. Olivia, did you get a chance to watch any of this coverage? Is it being talked about at work and things like that? Olivia's probably walked off. We're not seeing typing from her there, so she mightn't be there. But in any case, you can let us know on the forums. Any of the rest of you, did you have an opinion? What do you think? Do you think we'll be we'll be seeing self-driving robo-taxis on the roads next year. What do you think? Tokyo Olympics, yeah. Well, I mean, again, that's a very confined area that I think they're going to use it there, fixed space, or what they call geofencing. And what they were saying is, no, it's not a robo taxi if it's geofenced. So they weren't taking that as being the thing. So this idea that it can pretty much go anywhere, it'd be great. But I'll believe it when I see it, I think. Okay, guys, listen, I think I'll leave it at that. And if you have any questions, obviously put it up on the forum in the meantime. Sorry that we couldn't have had our guest lecturer. I'm sure it would have been excellent if we could have had it, but it can be difficult when people are obviously working in a very difficult industry to always get the time free to give that to us. And I know you have had some very good ones over the years, so sorry we couldn't bring you another one on this one. Okay, good night, guys.